Thank you very much. Awesome. Right, so we tested this yesterday, of course. So what I'm going to do here is, they said we're going to cut down from 97 to 5. So take 5. A countdown of what's essential in software development. Please do not walk away thinking that this is some kind of magic list. There are no silver bullets. This is just 5 things that I thought were kind of interesting, that I noticed in my own teaching, my own writing, and my own advice. I found that there are certain things I often kept offering, and then I noticed that they all count down. In other words, I have something with 5, I have something with 4, I have something with 3, and I just thought, perfect, this is a talk. The term Take 5 was popularized in 1959 by the Dave Brubeck Quartet. It was actually Dave Brubeck asking Paul Desmond, he said, all of jazz is written in 4/4 and 3/4 time. Let's do something really different. Could you write me something that's in 5/4 time? So 1, 2, 3, 4, 5, 1. And that gives it its characteristic rhythm. And this completely changed the face of jazz and our perception of what popular music could also be. We also use the expression take 5 to refer to 5 minutes. I'm going to take longer than 5 minutes to do this. We can also see that I'm going to look at ideas rather than music or minutes. If you write it in Haskell, we're going to take 5 ideas. If you write it in .NET, we're going to take 5 ideas. The first one, I'm going to count it down. 5. 5 orders of ignorance. Now, just a moment ago, Lucien was talking about learning. What is learning? Well, that's kind of an interesting question. Learning it's knowledge acquisition. It's knowledge communication. There is something in what we do in software development that ends up getting it classified as knowledge work. Now, when I was younger, I used to think this branding, what is it that you do? I'm a knowledge worker. It sounded ridiculous. And then after a while, I realized that at a deeper level, it is true. That is what you're doing. In a code base, quite literally a code base is a codification of knowledge. It is a codification of the knowledge of this is my understanding of the domain, of the problem, and the domain of the solution, and how we can bring the two together. You are codifying this. You are constantly learning, and you're constantly trying to communicate through the code. And you're doing this collaboratively as a team. In other words, a code base is effectively an executable Wikipedia. It's a collaborative knowledge exercise. So this takes us in a very different direction to thinking about code as just being about solving business problems, or code as a kind of a product. It's a collaborative knowledge exercise. And the great Grace Hopper made the observation, to me, programming is more than an important practical art. It clearly is that, but there's something else here. It is also a gigantic undertaking in the foundations of knowledge. It is kind of like applied philosophy. So if you're looking for something extra to put on your business card, and you're thinking, software engineer is a bit boring, full stack developer, applied philosopher. Okay, that's way cooler. So we should be humble about what we know and what we don't know. There is this quote, you will find it, sometimes you will find it on business kind of memes. It dates back a long way. We think, I know that I know nothing. Normally, Socrates. Except that people actually, when you look at it, it's just like, actually, we don't know if he said that at all. So we don't know if he said that he didn't know. That's a very meta level of knowledge, which takes us into the 5 orders of ignorance. Philip Armour in 2000, in Communications of the ACM, wrote this up. And I was quite deeply affected by it because I thought this is a really interesting way of thinking about what it is that we do, organizing our knowledge into different zones, classifying the nature of what we know. Of course, this being software development, he counted from 0. Lack of ignorance, lack of knowledge, lack of awareness, lack of process, meta-ignorance. I'm going to go through the first 4, but I don't need to go through the 5th one. Meta-ignorance basically means you don't know about the 5 orders of ignorance. We're going to solve that problem, so let's get rid of it. I'm also going to use slightly more specific terms. The known knowns. The known unknowns, the unknown unknowns, and the unknowable unknowns. Every now and then, whenever I present the 5 orders of ignorance, I get somebody either asking me if it's in the room, or they email me. I had one the other week where they said, Kevlin, what about the unknown knowns? They're already up there. Okay, it's already handled. This is what we know. Sometimes what people are trying to say, what about the things that I know, but it turns out that I'm wrong? Those are the unknown unknowns. We'll get to those in a minute. Yeah, this is about what you know and can demonstrate. So let's talk about the known knowns. These are the things that you know that you know. Okay, and it's very simple statements. It can be very much like, yep, okay, I know this programming language to this level of competence. I know this library. I am familiar with this domain. I know that, okay? I know that I know how to speak English, but I also know that I don't know how to speak Romanian. There are known unknowns. There are things that we don't know, and we know that. There are boundaries. If somebody said, you know, here is a programming language that you've not used. Do you know it? No. Oh, that was easy. And we acknowledge that. Now, the interesting thing is we already have a bias in this level, but at this level, this is the one we're comfortable estimating at. We're kind of comfortable estimating some of the things that we know we don't know, but we kind of make them a little less important, because if they were important, we would already know them, of course. So in your brain, you kind of fall into this trap of saying they're less important, but at least you've acknowledged that you don't know something, that there will be work that you have to do to achieve that knowledge. And that's fine. The problem is that most of software development does not happen in 0 and 1. It doesn't happen just with the known knowns and the unknown unknowns. This is where we walk into the unknown unknowns. You did not know that you did not know. How do you plan for that? Actually, there are some ways. We can't plan for it, but what we can do is increase the probability that we will discover. This is where things like bugs live. This is where assumptions live. This is where, when you thought you knew something, and then one day you wake up and you go, I was wrong. You did not know that you did not know that you were wrong. Yeah? And when I talk about things like bugs, that's quite important, because it affects defects of any kind will affect a development process, whether they are small bugs or larger issues of development, because they're very difficult to anticipate. I mean, if somebody today asks you, how long is it going to take you to fix the bugs that you put in the code next month? What? I mean, what am I supposed to do? Sit there next month going, right, here's a bug, I'm going to put it right here. Here's another bug, I'm going to put it there. Let me think, it took me 5 minutes to put in, should take me 5 minutes to take out. No, it doesn't work like that. The whole point about this level of knowledge is that it's surprising, even when you're expecting it. From a knowledge point of view, epistemology, so more philosophy, it's a little bit like, and if you've not yet had the experience of stepping on a Lego brick with bare feet, it's not one I would recommend, but it's certainly one you remember. It's a little bit like somebody saying, okay, here is a dark room. You have bare feet, there are Lego bricks there. Even if I tell you you have assumptions, you won't know where they are until you step on them. Assumptions are very curious pieces of knowledge, because they are discovered by contradiction, mostly. And what do I mean by that? Normally, you discover you have an assumption when it's wrong. You don't really discover when it's right. You have a chat with your colleague and they say, oh, no, you're not supposed to reconnect at that point. Or actually, the last one is a dummy record that's put in for legacy purposes. And at that moment you say, oh, I had assumed that. At that moment, you now know what you did not know was wrong. Okay? It's very difficult to discover that, which means it's really funny when people say, okay, give us a list of your project assumptions. Hang on, let me just get in a time machine and travel to the future. The best you can ever do is say, our assumptions so far that we have discovered. Sometimes going into something, you can state an assumption. But there's a whole load of stuff that's in the unknowns. But what can you do to increase the probability you discover it? Well, we'll get to that in number 4. We want to increase the probability of discovery, especially when it comes to bugs and things like that. You know, you always get these discoveries when people confidently say in the news, you know, it doesn't matter if it's about AI or something like that, or just regular, more regular conventional software. There's always a surprise, there's an outage, there's an issue. They did not know that they did not know. This is where bugs live. This is quite an interesting one. Driverless race car drives straight into a wall. This happened 2020. Best bit, during the initialization lap, so the car is going round, it's supposed to be self-driving, something happened which apparently caused the steering control signal to go to NaN. And subsequently, the steering locked the maximum value to the right. This is absolutely fascinating. The point there is that somebody did not have a check because they did not know that this was a possibility, because somebody probably said, that will never happen. And so they don't have a check for that. You can't even see it. Actually, one of the funniest things is when I retweeted this a couple of years ago, it's got to the point that JavaScript is so common that people think that NaN comes from JavaScript. And somebody says, oh my goodness, they are using JavaScript in cars. Actually, yes, they are using JavaScript in cars. You should be very afraid. But not here. Not in the engines. This was actually MATLAB. NaN's that goes back to the 1980s. Okay, let's talk about these guys. These are really interesting. Unknowable unknowns. What does unknowable unknown mean? It means there is nothing that you can do to find out something before it happens, before it can be known. I can't do something else like do more testing, do more code reviewing to discover this. There is no process by which I can discover something sooner. And this is particularly relevant when we talk about time and events. And the observation here, you may have come across this quote, prediction is very difficult, particularly or especially about the future. What I like about this quote is that we don't know who said it. I used to think it was Niels Bohr, and I still like the Niels Bohr interpretation, but my co-authors a few years ago, they preferred another source. And, you know, there were 2 of them and 1 of me, so we chose the other one. The thing is, I've looked into this. It turns out we don't know who said this. And this was the past. This is stuff that's already happened. How on earth are we supposed to anticipate the future? Humans struggle with the future. We come up with ideas like roadmaps. It's such a popular business metaphor. It's found its way into software development. We have product roadmaps, architecture roadmaps. You know, I think roadmaps are a really good idea. I think they're a great idea, but you need to understand what a roadmap is, because people are doing it wrong. You can actually go online and just Google roadmap PowerPoint template, and you will find loads of possibilities. And they often show a road. And they show, you know, here's where you put all your stuff, you know. This is where you put, you know, this is where you put your first goal. This is where you put your second. And you go through, and it's just like, yeah. And it looks really tidy and impressive, particularly if you're giving a presentation. There's only one problem. This is the centre of Bristol, where I live. It's in the west of England, 200 kilometres west of London. That is a roadmap. There are a number of interesting things going on here, but I'll just keep it to one observation. There's more than one road. Why would you have a roadmap with only one road? What is the point of a roadmap with only one road? That's just an itinerary. That's not a roadmap. You see, that's why I say I think roadmaps are a great idea. I wish people would use them. Here is the one road. What, that's it? You've only got one future? There's only one road? The whole point about the future is that there are many roads. What you need to show people is this is our current thinking based on our existing assumptions. We're going to take this path. But you know, there's another path here, and there's another possibility. And we may also find obstacles. If you're driving around using an active map, taking live data, you may find this route is 5 minutes faster than your original route. Or you may find that there is a blockage, there is an accident or something on there. The whole point here is, yeah, this is what we want. One of the things I love about this is when I was Googling this last year, I found one that had the years marked out. Okay, hands up everybody that had in their plans and their roadmap for 2020, all of our work will be completely disrupted by a global pandemic that will change the nature of business and work forever. Yeah, nobody had that. This is an unknowable unknown. You cannot know it till it happens. This also has important implications for the way that people prioritize their requirements. There is this mantra in the Agile community, prioritized by business value. I have some very bad news for you. You can't. I'm not saying you shouldn't. I'm saying you can't. It would be great if you could. There's a very simple reason, because you do not know the business value of something until it has been built and shipped and used. If you knew the business value of something in advance, honestly, that would completely transform the nature of markets over the planet. We'd spend most of our time going, no, let's not do that. That'd be it. Hang on, I can see the future, we should do this, and be right. Most of the time we are wrong. The future is not knowable before it happens. You cannot prioritize by business value because it violates the laws of physics as we understand them. This is a really important detail. I've had people say, no, Kevlin, you don't understand Scrum or Kanban or whatever. No, really, I understand enough physics to tell you that time travel is not possible. And if time travel is possible, why the hell are you developing software? Why didn't you just go and see the dinosaurs? And other cool stuff like that. You can prioritize by estimated business value. That's different. You can certainly do that. But never confuse an actual with an estimate. Okay, so what we find out of the 5 orders of ignorance, and borrowing from Douglas Adams, is that we demand, and we've been given, rigidly defined areas of doubt and uncertainty. These are embedded into the fabric of computer science. There are formally undecidable things. There are things that cannot be determined. And this actually affects this is the halting problem, this is all kinds of stuff, Gödel's incompleteness. The universe also has these unknowable areas. Up until last week, my slide deck included M87 star. This is Sagittarius A star. It's a little closer to us. It's only 28,000 light years away, so it's practically next door. But that brings us to 4, which is a process one, the PDSA cycle. Now again, I'm not going to say you must follow this cycle religiously. It's not at all like that. I want to understand, first of all, how we got here. Back in 1968, there was a now very famous conference sponsored by NATO, Software Engineering Conference. It's often referred to in books. It's often misunderstood and misinterpreted. So a few years ago, I decided I would sit down and read all of the proceedings from that. It was a real eye-opener. Most of what people say about that conference was not true. And some of the things that we forget, it's like, wow. You know, I'm not saying that we had all the answers back in the 1960s, but honestly, there were some good observations that have taken a while to circulate in our industry. Let me observe this one. So J.W. Smith, he made the observation. He's working for a hardware manufacturer. I've only been 7 months with a manufacturer, and I'm still bemused by the way they attempt to build software. They begin with planning specification, go through functional specifications, implementation specifications, etc. This activity is represented by a PERT chart with many nodes. There are lots of different charting things, Gantt charts, PERT charts, all kinds of charts. If you look down the PERT chart, you discover that all of the nodes on it, up until the last one, produce nothing but paper. And you know what? That's a sign of progress. These days, we don't even use paper. Which leaves the sentence as, if you look down the PERT chart, you discover that all the nodes on it, up until the last one, produce nothing. But it's the closing quote here. It is unfortunately true that in my organization, people confuse the menu with the meal. And I think this is great as a piece of humor from 1968. But we took these ideas into the 21st century. It's not a new observation, as Andy Kinslow pointed out. The design process is an iterative one. It's a learning cycle. You don't learn all at once. You are gathering your knowledge. You're gathering your knowledge through a cycle of expectation and experimentation. So let me talk about the PDSA cycle. Plan. Here's a thing we're going to do. Here's a thing I want to explore. Here's a hypothesis or set of hypotheses that I want to examine. That's what we're doing every time we build a piece of software. I've got a great idea. Brilliant, let's try it. Ah, you know what? It wasn't so great. Or maybe we can make this faster if we use this optimization or this platform. Okay, let's try that. Ah, that didn't work out quite the way we expected. Or maybe it'll be easier to develop if we use this framework, and that would save us time. Okay, show me, let's try it. That's our anticipation. That's our suggestion, and then we do it. The problem is, historically, a lot of plan-driven approaches have stopped here. We do a lot of planning, and then we do an awful lot of doing, sometimes at the weekends, and that's it. But there's no cycle. And then sometimes people pick up the idea that maybe we should cycle. The problem then is that they go plan, do, plan, do, plan, do. And we're missing something. We're missing the ideas that we should take the feedback. Learning involves a corrective cycle. It involves reflection, study, and then a response. Here's what we're going to do based on what we now know. Repeat. Now, you may find there are variations of this. There are things that are very similar. There's Boyd's OODA loop, which I'm not going to go into, but is similar with slightly different objectives, but also applies in business contexts. I'm also not going to say that you should make these rigid and have, okay, we finish planning on Friday, Monday we do. You can do these concurrently, they blur together. But all four of these activities should be present. You can always just check back, are we doing this? What's difficult is that the lower half of this diagram is hard to see. It's very easy you can see when people are doing planning. Planning has an output. Whether we talk about, here's a plan for how we're going to build something, or here is a plan in time of who's going to do what. And doing, I can see the result of doing, but what is the result of studying and acting? It's almost invisible, yet so important. It doesn't have immediate consequences, it has long-term consequences, which is why the bottom half often gets ignored. Now, sometimes you will also see people call this check. Now, the original formulation comes basically from Walter Shewhart and William Edwards Deming. And the terminology was study rather than check. Check has been used in manufacturing contexts. I don't like the word check because it sounds fast. It's too quick. Just check it. Yep, checked it, done. Study sounds slow because it's supposed to be. It's supposed to take time. And there is also a refinement that Deming preferred in his later years, as I understand it, adjust. Because act is what's the difference between act and do? Adjust is about responding to reflection. So the author, Neil Gaiman, observed this. You have to finish things. That's what you learn from. You learn by finishing things. So this is how you increase the probability that you will find the unknown unknowns, because if you keep doing stuff, you're more likely to step on those Lego bricks. You will not discover those Lego bricks if you stand outside the room. You need to walk across the room. That's how you do it. You increase the probability of those. But we see this cycle all over the place. This is not about how big processes. This is about any kind of flow that is intended to deal with knowledge. Any kind of flow. Often when people talk about things like test-driven development, they talk about the test-first cycle, red, green, refactor. Yeah, I even teach it that way. But I also teach it this way, because I think red, green, refactor is not helpful. I regard many of the interesting things in software development as a process of inquiry. I'm trying to discover things. I'm going to ask questions. What does success look like? Let me show you the code. I want this code to work. What is the simplest thing that could possibly work? Okay, let's just respond to that need that we've created in a simple way. We know we're going to make it more complex, but only as necessary. And then take a step back. Do it slowly. Are there any gaps, repetitions, inconsistencies, trends, or questions? And then how would you address them? In other words, we could write it up like this. We can write it as test, code, think, refactor. This is exactly what we had before. Now, One thing we do have to be a little bit careful with, though, is an observation that we can borrow from this book, 101 Things I Learned in Architecture School. It's actually a book about architecture, building architecture. It's a lovely book. And about half the advice in here is applicable to any design-based discipline. And one of the observations that Frederick makes is this one. Properly gaining control of the design process tends to feel like one is losing control of the design process. That roadmap idea. What we're doing is we are saying, there are a whole load of things that I don't know, and there are a whole load of things that I don't know that I don't know. But that does not mean I can't make progress. I can always make progress. What you do is you have a meta plan. Here is the way that we will organize our work and how we respond. And we will do it in a way that we can react quickly. Unfortunately, that's not completely the way that the industry has gone. So, Voltaire made this observation about the Holy Roman Empire a few years before the Holy Roman Empire was dissolved in the 19th century. This body which was called and which still calls itself the Holy Roman Empire was in no way holy, nor Roman, nor an empire. And I think this applies to the scaled agile framework, which is in no way scaled, nor agile, nor a framework. People use it because it feels safe, but it doesn't feel like you're losing control of the design process. It's not designed to be adaptive. It's not actually particularly agile. This is a word that gets used and thrown around a lot. And actually, it has a very simple meaning. Okay, let's go and have a look. Now, I don't want to do, the dictionary is not a source of truth as to what should be. It's a source of observation about what has been. If I use the word agile in English, the default meaning is that you are able to move quickly and easily. That's the idea. That's why the word was coined. It's actually one of the better words that has been used to identify a movement within software development. Because it's good. It actually characterizes what you're after. It's also an adjective. Now, why is that important? It means it describes the property of something. It's an observation. You can't do agile. You can be agile. You can be more agile or less agile. You can be more agile than you were 6 months ago. That team can be more agile than that team. It's an observation you make about something. You can also apply it to a code base. Is that an agile code base? And that's not some kind of fancy branding. Are you able to move it quickly and easily? If the answer is yes, well done. If the answer is no, that's where our work should be. In fact, that's where most of our work is. The problem is there's a lot of people doing agile. The way that a lot of organizations are trying to embrace it is they two ideas is far too complex. Let's just have quick movement. Don't worry about easy. And the effect of this, unfortunately, is that we end up being very busy. And that wasn't the goal. So we have an obsession with speed, or people phrase it as velocity. Now, velocity has a number of meanings in English, one of which is speed. But given that we're in a technical domain, I'm going to use the technical term for velocity, because velocity has a much stricter technical interpretation. To understand why this is important, because I really do wish that teams would measure velocity, but they don't. They just measure speed, which is a rate. To understand it, the rate at which you are making a difference in some direction is your speed. But the direction is really important. The combination of the two is velocity. Because at the moment, we have lots of teams obsessing over measures and lots of organizations obsessing over measures. How fast are you going? We're going really fast. Are you going fast enough for the customer? I don't know, but it's really fast. Okay, it's like German Autobahn fast. We are going fast. What direction are you heading? We have no idea, but we're going to go really fast. You guys are heading north at 150 kilometers per hour. Yeah, really fast. You should be heading south. Yeah, I know, but we're going fast, aren't we? And that is most teams. You'd be better off walking in the opposite direction. The goal here is not speed. We keep talking about doing things faster. Actually, we shouldn't be talking about faster. It's not the same as what we actually want, which is sooner. Sometimes you get somewhere sooner in time by going fast. At other times, you just think about your route a bit more carefully, and you, instead of being busy, you go, that's a shorter route. It takes less effort. You're supposed to be doing that, not looking busy. So sooner, not faster. Whenever I see the word fast on something, I always think, did we really mean that? So there's a kind of concern there. Let me talk about 3 questions for architecture. Now, there's a lot of different ideas about what we mean by architecture, and indeed Martin Fowler captured this quite nicely by saying, it's a term that lots of people try to define with little agreement. There isn't one true source where we found the person who used the term first. We can find, in many cases, we can find certain vocabulary. We can say, this is where this idea came from. Here is where the word DevOps came from. Here is where microservices originated. We can find a point of origin and then see a line from there. But architecture is such an obvious and common metaphor. We find people have applied it creatively from many different sources, and sometimes they don't mean the same thing. The earliest I've found is 1969 as an explicit reference to software architecture. So if you know any earlier ones, I'd love to know, because it turns out it's been in use for a very long time. But what does it mean in that case? Well, we don't have a true definition, but there are definitions that are more or less useful. One of the ones that Martin observes, one is the highest level breakdown of a system into its parts, the big picture. The other, decisions that are hard or expensive to change. Now, I don't generally go for the first one. People often will put up a PowerPoint diagram and say, this is our architecture. The one thing I can guarantee you is that if somebody puts up a diagram and says, this is our architecture, the one thing I can tell you is it is not their architecture. It is a view of their architecture. It is a representation of their architecture, but it is not the architecture. It normally involves a bunch of boxes with relationships. It often misses out things like time. It misses out smaller details that actually go up to create how the system fits together, that if you were to try and change those, would be enormously difficult. And those define the architecture. I actually had this with a system where somebody said, I asked, we were talking about the architecture, and I said, is this a multi-threaded system? And they said, you don't need to worry about that. That's not part of the architecture. I said, well, multi-threading is how you define time for a system. You are defining the laws of physics for your system, and you don't think that's important. It's an implementation detail. Trust me, if you've ever tried to change a system at the whole level, if you change the nature of time in your code universe, strange things happen. It's deeply, deeply, profoundly architectural. Architecture is not about space on its own. It's about space and time. So let me give you those 3 questions. I'm taking these from a book by Paul Dyson and Andy Longshaw. This book is now 15 years old, so I'm offering you a suggestion of wisdom that comes from the beginning of the book, because clearly the architecture of internet systems has changed hugely in a decade and a half. But near the beginning of the book, they offer this simple idea. Our position is that an architectural definition is something that answers 3 questions. And you'll see there's a kind of a theme here. I like this idea of questions, because they move us forward. We're obsessed with answers, but if you have good questions, those will keep you going for much longer. The first question is, what are the things, what are the structural elements of my system? How are they related in space and in time, and in protocol, and in calling convention? What are the things, the functions, the classes, the objects, the processes, the services? What are the things that you would draw as a box, and then how do you relate them together? By function call, by asynchronous call, by a network call, by using this protocol or that protocol. We're describing how we fitted everything together. And then the last question is most important. Why? Why is it like this? What's the rationale? What design principles do we use? What history did this system give us that got us to this point? So in other words, it really is a very simple case of kind of 3 questions. So we'll move from 3 questions to 2 questions. 2 questions of quality. How do we know that something is good? Well, it kind of depends on the nature of the thing. If it's food, then we have a very specific way of describing what we personally, individually find as good. But if we are dealing with a software structure, we often talk in terms of problems. Oh, we've got a problem. Okay, let's do this to solve it. That's a different kind of good. That's not, that tastes great. That is, yes, this fits, this is appropriate. And this is why we care about this, because often people end up with this idea of like, oh, we don't worry about the architecture, or we don't have enough time to worry about the architecture, or our architecture is emergent. Yes, you can have an emergent architecture. It takes a lot of effort. It's not that you can't do it, it's just you don't get it for free. Teams that have successful emergent architectures are highly, highly creative and genuinely agile. Oh, let's try this. Well, that's terrible. Let's not do that. I've got another idea. Let's do that. Ah, brilliant. So that's the point. But they're also asking the question, what is the thing that we're building and how are we building it and how can we make our future lives easier? So this book was a huge influence to me. I got this in 1993, Times Way of Building by the late Christopher Alexander. This is, Christopher Alexander originated patterns, the idea of patterns that eventually made their way into software. This was actually about buildings, but he defined very much, there's a lot of really interesting ideas in the patterns, in the space of patterns, that people kind of never picked up on or never lost. And there's a thinking model. For me, one of the most important passages was this one. We know that every pattern is an instruction of the general form context, the situation in which we find ourselves, that characterizes it. If we're dealing with code, it might be, I'm working in this particular programming language, and there are lots of threads. You know, I'm working in Java, it's a multi-threaded code base. All of the code is in a single executable, okay, single process space, yeah? That context is very different to, we are running a JVM system, but there are multiple languages in use executing in different processes, and we are using HTTP to connect things with a whole load of JSON thrown between them. Both of these are statements of context, as well as statements of connection and composition. The idea is, where are you? This is the situation you find yourselves in. Then, conflicting forces. What is it that makes the problem you're experiencing a problem? What is the difficulty that you're having? And then configuration. By configuration, do not confuse that with the idea of configuring an application or the configuration file or anything like that. This means configuration as in, what solution structure do you propose to solve the problem that you've got? And Alexander said, we say that a pattern is good whenever we show that it meets the following two empirical conditions. These are the, one, the problem is real. Two, the configuration solves the problem. Now this feels like really, really obvious. I mean, painfully, childishly obvious, which is why it's so powerful. Because this is actually not really about patterns. Patterns is more to do with recurrence. What he was describing and what I discovered so incredibly useful was he was talking about design. It doesn't matter whether it recurs. It doesn't matter whether this is an idea that we can use elsewhere in different forms. He actually described for me an understanding of design. We are solving a problem in a particular situation, and we have a particular solution. Is it any good? Well, was the problem real? Sometimes use this as a review question, because sometimes I've been shown, here's our architecture, and here's our, we did this, we did that. Oh, what problem does that solve? And people just look at me. It's just like, oh, he's asking a really difficult question. It's a really hard question. Why did you use XML here? We don't know, because everybody else was using XML. I don't know. I mean, literally, that was the answer I got in a project a few years ago. Why are you guys using XML? It's completely inappropriate for the class of software you're dealing with. Because everyone else is using XML, and we haven't used XML yet, and it will look good on my CV. Were they actually solving a real problem that they had? No, they'd already solved it with something much simpler. The problem they were solving was we don't have XML on our CV. So we are very good at solving imaginary problems because software development is a creative profession. Therefore, we have great imaginations. And the more creative you are, the more extra stuff you end up solving. What if this happens? Good question. What if that happens? Remember all these paths into the future? The more imaginative you are, the more bloated and complex your code will be, even if that future never arrives. Because the other question you need to ask is, what if it doesn't? What if it doesn't happen? What if that's not actually a problem, only in my head? Put it on a watch list. Put it to one side. Make a note of it. Never throw your knowledge away, but that doesn't mean you have to encode it and put it in the code base. But the other thing is, does our solution solve the problem? Again, that's a really simple idea. I mean, that's what we're saying. It's a design, it's good. When people say the same for practices, we're going to use this practice. Why? Because we have this problem. Great. And how's that working out for you? Oh, well, we never checked. PDSA. You've got to study and then adjust. We proposed a solution. Did it actually work out? I mean, that really is all this is. 2 questions. Whenever you are making a decision about your practices, your designs, your code, and you perceive there's 2 different ways to go, ask the simple question, am I solving a real problem here? Have I understood it well enough? And does the thing that I am suggesting actually solve it? Because sometimes we like an idea and we want to put it in the code. I think we're all guilty of that. I've done that. It's just like, I want to use this technique. Where can I put it? What problem does it solve? It solves the problem that I've just discovered this and haven't put it in code yet. Yeah, that's the only problem. So, have we solved it? Is it real? We need to make sure that we don't fool ourselves, because we're very good at doing that. We sometimes have to check with the little questions. Use those 2 questions in reviews and with yourself and your colleagues. So the final one, have more than one idea. What do I mean by that? It's a quote that I use a lot from Émile Auguste Chartier. Nothing is more dangerous than an idea when you have only one idea. Now, this is not just good for software. This is actually quite a good way of looking at life. But sometimes we get really attached to a particular design approach. And that becomes the only way we see the world. I had a client many years ago, and they had the problem of first fit. What do I mean by first fit? Whenever you asked this particular team, in fact, it's true across many of their teams, whenever you asked them, okay, how should we do this? They'd go, oh, here's a way of doing it. And then, yeah. And they'd stop. And that would be it. And I remember I learned how to work around this. I said, once when somebody did it, I said, okay, that's 1. Give me another one. But Kevlin, we've just given you a solution. Yes, you have. We haven't tried it yet. We don't know if it's any good. We need more to experiment. If you only have one idea, that's no good. It's a start, but you need to get to at least 2 and preferably 3. Because then you can evaluate by comparison. You have different hypotheses to entertain. You know, if you can think of 2 or 3 different ways, if you can think of only one way of doing something, then maybe you haven't understood it enough. That tells you that. That's really useful at that point. When you have 2 or 3 different approaches, it's just like, you know what? Now I can evaluate. I can see which might be better. Okay? So this is a really important thing. Whether it's a practice, even if you believe in a particular practice or coding approach very, very strongly, always take a step back and look, what do the other approaches say? What else is available to me? Take that step back. So, in case you wanted a slide where everything is summarized, here is a slide where everything is summarized. Here are the 5 things. Understand what you know and what you don't know, or rather the nature of what you don't know. It turns out we are always working with incomplete knowledge. You will never know everything that you need to know to do the work that you are doing. Give up that idea completely. But that doesn't mean you can't make progress. Every day when you get up in the morning, you are capable of getting through to the end of the day. Well done for being human. It's a superpower. We are always able to make progress, but that doesn't mean we have to know everything. But we can increase our knowledge, and we can make sure that what we suppose we know, we do actually know. Make sure that you're always checking back. That's the value of the PDSA cycle. It's not a specific steps in the cycle. It's the idea that you're always checking. when you look at the architecture or the structure of something, be sure to look at the what's and the how things are connected, but also try and understand why. That's almost invisible when you look at code. Why is this like this? There's probably a reason. It could be by accident. It's like this because we didn't know any better, but it could also be like this because we had a very specific problem we were solving. You need to know the difference between these two. And you also need to be able to judge a design or a practice or an idea. Is it any good? Well, if it's to solve a problem, is the problem real? And have we solved the problem? And entertain more than one hypothesis, more than one approach, more than one paradigm, more than one methodology. Thank you very much.